Professor Daniel Mashau, Executive Dean of the Faculty of Engineering and the Built Environment. Professor Nnamdi Nwulu, our inductee this evening. Professor Michael Rudolph, our Director for the Center for Ecological Intelligence. Senior leaders of the university, members of Senate and other academics, distinguished guests, ladies and gentlemen, Sanibonani, Goeienaand, good evening, Thobela. It is indeed a great honor and a special privilege for me to welcome you to the Professorial Inaugural Lecture of Professor Nnamdi Nwulu. As I do so, I wish to express a warm welcome to his loved ones, special guests, and his colleagues. This is indeed a proud and joyful, yet a landmark moment for all of you, for Professor Nwulu, and of course, for all of us here at UJ and higher education in South Africa and beyond. An inauguration of a professor is a public ceremony in which newly appointed professors are inducted into office by the Vice-Chancellor and deliver their inaugural addresses. The ceremony has its roots in the medieval university and serves multiple purposes. Firstly, it is an expression of welcome and an entry for new professors joining the circle of colleagues who are already professors. Secondly, it provides a platform for the professors to display their expertise in the discipline and showcase their research. In isiXhosa, we say, ukuthweswa isidanga, kwisigaba sobunjingalwazi. This, loosely translated, refers to assuming the role of the professor. Of course, in colonial traditions subscribed to by universities, this refers to the gown and the cap. Traditionally, the wise one would accept a blanket, ingubo. Once we have listened to the inaugural address, the gown or ingubo denoting the professorship will be formally assumed. Today, we gather to bear witness to the entry of Professor Nwulu to the illustrious community of scholars at the university. It is a celebration of the contributions to the discipline and ultimately the impact on society. Professors provide a university with its identity, character, and academic legitimacy and integrity. The inaugural lecture is a rite of passage following the confirmation of the appointment of the person as a professor. This evening, we will listen to Professor Nwulu as the gown goes to town. By this, I mean that the power of the inaugural address is where the expertise is showcased beyond the corridors of the university and reverberates with society. It stands out as a moment of pride for the incumbent, the family, fellow scholars, the university, and ultimately society. For the German philosopher and diplomat Humboldt referred to a university as the whole community of scholars and students engaged in a common search for the truth. Newman talked about teaching universal knowledge. Universities have been viewed as instrumentalists serving the purpose of the economy or utilitarian in purpose. I would hope that we can break out of these narrow conceptualizations on the university as contributing and reflect on the university as contributing to the public good. Edward Said, in an article on defiance and taking positions, offers a formulation of the ideal role of the true intellectual as one who commands a vast knowledge of his or her discipline, who is rigorous in the analysis of literature, who views being an intellectual as a vocation, the intellectual who considers it necessary to step into the public sphere and to speak truth to power, namely to question, interpret, and understand authority rather than consolidating it. To step out of the boundaries of the academy, to connect oneself, to affiliate oneself, to align oneself with an ongoing process or contest of some sort, perhaps with the aim of improving the lot of the oppressed. The intellectual who functions as a kind of public memory to recall what is forgotten or ignored, to make the connections that are otherwise hidden, and to provide alternatives for mistaken policies. It remains then for us as a university with a Pan-African vision to derive our mandate as intellectuals and as professors. How do we embrace the role of a professor as a disruptor while continuing to be flagship carriers of our disciplines? This evening we will listen to Professor Nwulu as one step further in the journey of being a professor. This is a journey which does not culminate once this lecture has been given. It is a self-reflective pause in the journey of the professor, with a promise of more to enrich our minds and simultaneously contributing to the rich intellectual body of work in the discipline. And now, ladies and gentlemen, let me invite our Executive Dean, Professor Mashau, to introduce Professor Nwulu. I thank you. Ke a leboga. Ke a bonga. Bye, thank you.
It's indeed a great pleasure for all of us to be here today to witness this moment that we are witnessing now. My task is to let you know a bit more about Professor Nwulu. So I'll be going through his CV so that when he wears that gown, you do know where he comes from and the road he has traveled. Professor Nnamdi Nwulu was born in Lagos Island, Lagos State, Nigeria. He obtained a BSc in Electrical and Electronic Engineering from the Near East University, North Cyprus, in June 2009, graduating top of his class and was the International Students Valedictorian. He obtained an MSc in Electrical and Electronic Engineering from the same institution in June 2011, graduating with a distinction. As a postgraduate student, Professor Nwulu was a member of the Intelligent Systems Research Group at the Near East University. Prof. Nwulu proceeded to the University of Pretoria in Pretoria, South Africa, in February 2012, receiving a full scholarship from the National Hub for Energy Efficiency and Demand-Side Management at the University of Pretoria. He completed his PhD program in 2015 and graduated in April 2016. Prof. Nwulu thereafter secured employment at the University of Johannesburg, South Africa, in May 2016 as a senior lecturer in the Department of Electrical and Electronic Engineering Science. He was promoted to Associate Professor of Electrical Engineering in May 2018 and promoted to the full Professor of Electrical Engineering in May 2021. From these timelines, Professor Nwulu rose through the ranks to a full Professor of Electrical Engineering after 5 years post his PhD. During this period, he has completed the deep dive in blockchain, linking economics, technology, and law program from the University of Zurich in July 2020 and the emerging leader in the leadership development program from the University of Johannesburg between September 2019 and February 2020. Within these 5 years, Professor Nwulu has been extremely productive and impactful as an academic, winning the Phoebe Highly Productive Associate Professor Award in 2019. Prof. Nwulu is currently a professor of electrical engineering and the director of the Center for Cyber Physical, Food, Energy, and Water Systems. Professor Nwulu also holds the Coronet Blockchain Research and Innovation Chair and is included in the latest World Top 2% Scientist ranking published by the Stanford University. Prof. Nwulu is also listed among the Scival Top 500 authors by the Scholarly Output in Africa from 2016 to 2021. In prior years, Prof. Nwulu's initial research focus was in the power and energy systems field, specifically focusing on the system operations and control issues like dynamic economic emissions dispatch and demand-side management, electricity markets, and renewable energy integration. Prof. Nwulu's research focus has extended to food, energy, and water systems, and the inherent nexus between all three. This is important because Africa faces significant challenges in these three domains, and research can and should provide solutions. Specifically, the research focuses on food, energy, and water thinking, digital technologies, mathematical optimization techniques, and machine learning algorithms in food, energy, and water systems. This research focus has produced 5 books, 3 inventions, and over 170 publications, including 70 in index journals, winning him the 2021 NRF Research Excellence Award for Early Career Emerging Researchers in the Engineering and Technology category. He was also a 2021 T.W. Kambule NSTF South 32 Award finalist in the Emerging Researcher category and won the 2020 UJ Vice Chancellor's Most Promising Young Researcher Award. He is a member of the prestigious South African Young Academic of Science. Prof. Nwulu has been a recipient of several research grants from the NRF, from TIA, Technology Innovation Agency, ESCOM, TESP, and the European Union Erasmus Plus Mobility Scheme. From the private sector, Prof. Nwulu's research has also been supported by Biosec, SEL, Coronet Blockchain, and AIMS Netherlands. Prof. Nwulu has an exemplary track record in developing and transforming research capacity in South Africa. To date, he has supervised 11 PhD candidates completion with 2 students' theses under examination and is currently supervising another 10. In addition, he has supervised 8 master students to completion and is currently working with another 5. He strongly emphasizes developing independent scientific thought among his students and preparing them to become internationally competitive through international conferences, UJ postgraduate internal seminar series, and the doctoral and master's academy he organizes every year. He also encourages them to sharpen their skills in diverse research methods to facilitate their work in multidisciplinary environments. Prof. Nwulu is a professional engineer, registered with the Engineering Council of South Africa, a senior member of the Institute of Electrical and Electronic Engineers, a senior member of the South African Institute of Electrical Engineers, and a Y-rated researcher by the National Research Foundation of South Africa. Prof. Nwulu has served as a reviewer for many local and international journals and as a guest speaker at many academic forums, both locally and internationally, and also acts as a guest editor to reputable journals. Prof. Nwulu is the editor-in-chief of the Journal of Digital Food and Water Systems, associate editor of the IET, Renewable Power Generation, and the African Journal of Science, Technology, Innovation, and Development. What I've read to you, ladies and gentlemen, is a very amazing history of what he has done to date, and we really want to thank you, Prof, for providing us with this. Thank you.
Good evening to the good evening to the distinguished guests present in chamber and to the distinguished guests online. A special acknowledgement to the senior leaders of the university, Ms. Nolwazi Mamorare, the Vice Chancellor Functionary. Thank you for being here. Professor Daniel Marshall, the Executive Dean of the Faculty of Engineering and the Built Environment. Thank you for such a nice introduction. Professor Michael Rudolph, the Director of the Center of Ecological Intelligence. Thank you for agreeing to serve as the respondent. And then a special word of acknowledgement to my family and friends present here and those online, my colleagues, my students, both past and present, and those that I know are following online. Thank you very much for being part of this occasion. Professorial addresses are not the easiest of tasks. There is the pressure to sound professorial, right? To show that you actually merit the position that you are holding. And then there is it's further complicated by the fact that you're speaking to a much wider audience than you would have normally been speaking to. Normally you're used to speaking to those that are in your domain, right? And then the third complicating factor is the fact that you have to do this in a very short time frame, in 40 minutes. So it's a very difficult task. But what I'll be doing today is I'll be taking the advice of my wife, who told me that just speak so that our 5-year-old daughter can at least understand what you're saying. So that's what I would try to do. So you would hardly see any mathematical equations or things that are complicated. So hopefully it will be something that will be easy to follow. I will just basically detail some of the work I have been doing over roughly the past decade, and then offer some reflections about some of the results we have obtained. And then I would take out some time to thank those that have worked with me on this journey, right? And then the title of my address is Creating a Bulwark for the Perfect Storm Using 4IR Technologies. And then the outline is I would begin by unpacking what the perfect storm actually is, and then I would move and describe what the food, energy, and water nexus entails, and then we move to what is the fourth industrial revolution, and then we describe in better detail the bulwark for the perfect storm that we have been constructing over the years. We'll look at case studies and results that we have obtained, and then I would offer some reflections and future work. So what is the perfect storm? The phrase "the perfect storm" was actually coined by Sir John Bedington, who was the United Kingdom government's chief scientific officer advisor from 2008 up until 2013. And essentially, the phrase refers to the simultaneous shortage of food, energy, and water resources on a global scale, right? And then Sir John postulated that the perfect storm would make a landfall at around about 2030. So right now we are just experiencing the gathering storm, as it were. And then he says now it's not going to be a complete collapse, but things would be extremely worrisome. And then I think we are seeing symptoms of the impending storm, right? You hear about zero water in Cape Town and so many other challenges in the food, energy, and water space. And then it is characterized by energy insecurity, it is characterized by food insecurity, and it is characterized by water insecurity. And it is triggered by a host of factors, including global population growth, climate change, and the activities of man that harm the environment, that are unsustainable. the question now is, how bad is this storm at this stage, right? And I will be looking at key statistics. I won't peruse all of them, but a few show now that in 2022, about 690 million people are undernourished globally. When you're looking at food statistics, about 811 million people go to bed hungry every night as at 2022. There will not be a significant change by 2030. It is expected that by 2030, 600 million people may still face hunger in 2030. That's the period when the storm is supposed to make a landfall. From the statistics, it is obvious now that the agri-food value chain depicted here is not working for most, right? The agri-food value chain typically follows the movement of food from production up until it ends at the consumer, and then the cycle repeats itself. And then it also shows that for most of the people in the globe, food security is not their reality. And what's the definition of food security? Food security, according to the FAO, is defined as the availability and access to sufficient, safe, and nutritious food to meet the dietary needs for an active and healthy lifestyle. So now, food security speaks to both the quantum, the quantity of food, and then the quality of the food, right? And then let's look at statistics for energy. It shows now that 597 million people in Africa, 132 million people in developing Asia, and 39 million people in the rest of the world do not have access to electricity. Again, there are a host of other statistics, but these statistics also show now that the electricity value chain isn't working for most, and for most people, once more, energy security is not their reality. Energy security is access to clean, reliable, and affordable energy services for a plethora of uses, cooking, heating, and the rest. Again, take note of the fact that it's access to it's not just access to energy, but it's the quality of the energy that they have access to. In the similar vein, in terms of water, the statistics are also there. I will not bother to go through the statistics, but suffice to say now that water security is not a reality for most people, and the urban water cycle depicted here, right, is not serving the needs of most. So after unpacking what the perfect storm is all about, which refers to food, energy, and water insecurity, the question now is, what is the antidote to the perfect storm? What is the solution, if you like, to the perfect storm? And then my research journey has been on the creation of a sustainable bulwark to combat the perfect storm. A bulwark is a defense, is a guard, is a protection against unsavory or unfavorable conditions. And the perfect storm actually demands a bulwark. And then my research journey over the years has been on the creation of a cyber-physical decision support system as a bulwark to the perfect storm. And what is a cyber-physical decision support system? What does it entail? In our case, it entails leveraging food, energy, and water nexus thinking, and also simultaneously leveraging 4IR technologies to make optimal decisions and then also generate cost-effective solutions for the perfect storm, or to combat the perfect storm. So in the next couple of slides, I will be unpacking what exactly is the food, energy, water nexus thinking, and what are 4IR technologies vis-a-vis the creation of a bulwark to combat the perfect storm. So now the food, energy, and water nexus, a very quick deep dive into it. It's an approach that recognizes that there are interconnections between food, energy, and water resources. It recognizes that there are interconnections, there are interrelationships, and there are trade-offs between these three resources. So energy is required to service the energy needs of the population. At the same time, energy is needed to extract, treat, and distribute drinking water. At the same time, energy is also needed for agricultural purposes. It's needed for food processing and for food production that's at irrigation stage, and for somewhere later on in the food value chain. Water is also required for the needs of the populace. Water is also required to grow food crops and also to feed livestock. Water is also required to cool power system plants in the power generation space. And then food, which is typically grown on land, agricultural land at this time is also needed to grow energy crops such as biofuels, which negatively impact food security. And land use decisions also impact water quality and availability. This interrelationship now shows that the approach of sectoral decisions in one sphere, that's either in the food sphere or in the energy sphere or in the water sphere, doesn't lead to optimal decisions, right? So there is a need for a holistic approach or a holistic consideration of all three sectors simultaneously so that you are able to now better understand the interactions between these three resources, and you're also able to make better decisions such that you mitigate incidences of food, energy, and water insecurity. So that's the food, energy, and water nexus in brief. And then there is a relationship between the food, energy, and water nexus and the sustainable development goals. Now most of us should know what the SDG goals are. There are 17 of them in number. And you have 3 SDGs that speak to food, energy, and water resources. SDG 2 speaks to zero hunger, which is related to food. SDG 7 speaks to affordable and clean energy, which is related to energy. And SDG 6 speaks to clean water and sanitation. However, these SDGs seek to tackle issues of food, energy, and water individually, right? So the food, energy, and water nexus approach, therefore, is an important tool towards achieving sustainability, because the food, energy, and water nexus approach posits that the integrated consideration of these resources would lead to their better management. And therefore, it's a tool that should be leveraged more towards achieving the SDG goals. Now, let's move on to what is the 4th Industrial Revolution, right? I said now that the Bulwark leverages on food, energy, and water nexus thinking and 4IR technologies in developing sustainable solutions. So what is the 4IR, or the 4th Industrial Revolution? To begin, I would like us to unpack what an industrial revolution actually is. What is an industrial revolution? An industrial revolution basically is when there are major changes to society, to industry, to transportation, to life as we know it, stemming from the emergence of new technologies. All right, so these new technologies emerge, and then they essentially transform society and the way we live. There have been 3 industrial revolutions thus far, and we are now at the cusp of the 4th Industrial Revolution. Right, and this slide shows the prior industrial revolutions, the years they did occur, and the technologies that caused that shift in society. In Industry 4.0, in the 4th Industrial Revolution, cyber-physical systems are a key concept or a key characteristics of the 4th Industrial Revolution. And what are cyber-physical systems? Cyber-physical systems are systems that are controlled or monitored by computer-based algorithms, tightly integrated with the internet and its users. Essentially, in cyber-physical systems, the physical component and the cyber component are intertwined, right? There's basically a fusion of both components, such that there's a whole lot of interactions, and it's difficult to actually de-link those two spaces. And then the concept map of the cyber-physical system is shown here. But basically, I wouldn't delve too much into this. What I would just like to show is that the cyber-physical system requires a design methodology that supports validation and verification. And this is often done using modeling and simulation, which we do a lot, or which we leverage a lot of in our studies, right? And it requires feedback systems, possibly with economics in the group, humans in the group, environment in the group. That's essentially interrogating how these cyber-physical systems interact in the physical domain. And it has applications in a plethora of areas. In our case, we focus on its application in food, energy, and water systems. The technologies of the 4IR can be classified as either cyber or physical technologies. Some folks classify them as cyber, as physical technologies, and as biological technologies. But I'm of the view that the physical technologies also cover the biological technologies. And then I list a couple of technologies classified as either belonging to the cyber technology class or those belonging to the physical technology class. Right, and then, like I said before, the Bulwark essentially is a cyber-physical decision support system, and it leverages food, energy, water nexus thinking and 4IR technologies to make decisions and generate cost-effective solutions to combat the perfect storm. What are the specific technologies that we have used over the years in the creation of the Bulwark? We have leveraged significantly on data analytics, and then there are three kinds of data analytics, right? The first is either diagnostic or descriptive analytics, which seeks to answer the question, what has happened? What has been happening? What has happened? There is predictive analytics, which seeks to answer the question, what will happen, right? And then there is prescriptive analytics, which seeks to answer the question, what is the best thing that should happen, right? So prescriptive, predictive, and diagnostic or descriptive analytics. We have leveraged significantly over the years on prescriptive analytics, specifically mathematical optimization, considering either the classical optimization or the meta-heuristic optimization. And we've also leveraged significantly on predictive analytics, specifically using machine learning for our research to predict certain parameters well into the future. And we've also begun to leverage on IoT, Internet of Things, principally for monitoring and control, and also for automation. And then we've also begun to leverage on the use of blockchain technology, either public blockchains for writing smart contracts or private blockchains to integrate with Internet of Things technology. So this slide depicts the framework that we have been using for most of our research, integrating the food, energy, and water nexus thinking and 4IR technologies. And you basically have data that you obtain from various sources. Typically, it's secondary data, and that data is fed into our prescriptive analytics platform, which is built on mathematical optimization, and then you now obtain optimal decisions, right, based on the constraints and the various operating conditions that exist. You can also obtain this data from IoT, that's sensors that you deploy in the field, and you get either real-time data or much more practical data. And then you can also obtain data from predictive analytics, whereby you forecast the data. If you have historical data, you don't have correct data, and you forecast that data, and you feed that data into your prescriptive analytics platform, and then you obtain optimal decisions. Recently, we have also begun to leverage on blockchain technology, especially in areas where there's a lack of trust in transactions within the food, energy, and water space in terms of payments, in terms of settling contracts where there's a lack of trust, and those areas will benefit from the introduction of blockchain technology, which will provide transparency and immutability and other factors. So when you have the blockchain, some of those data is uploaded to the blockchain, and it remains there, and all parties can have a sense of ease about the transactions that they are participating in. Now, after obtaining optimal decisions, the next thing that should actually happen should be corresponding action, right? And then we've discovered now in our research that this gap is often not, this chain is often not achieved, and then there is a need to also study why you get optimal decisions, and due to a host of other reasons, maybe policy or economic reasons, those decisions are not actually implemented. And I would explain what we have done along those lines very shortly. So a specific example of our prior research leveraging food, energy, and water nexus thinking and 4IR technologies is shown here. We basically leveraged the technologies that I showed in the prior slide into food systems, water systems, and energy systems in a bid to achieve food, energy, and water security. Here we see a food system where we use here wireless sensor networks for a silo that's used to process food, to store food. And in this research work, we did some work, we've done some significant work on water quality monitoring, where we used machine learning algorithms to detect anomaly in water quality. And we've also significantly done a lot of work using prescriptive analytics for prosumers. In a power system, prosumers are electricity consumers that simultaneously produce energy and consume energy. And then there is the interlinkage between both systems, between food and water systems. In hydroponics and aquaponics, we've done some work using IoT in this space. In the nexus between energy and water systems in renewable energy power desalination, and then in the nexus between food systems and energy systems in biofuels production, and then the optimal siting and sizing of storage devices in a biofuel production system. We've also done a lot of work that looks at the nexus of all three. So an example here is an IoT solar-powered irrigation system, which basically touches on all three systems using 4IR technologies. Now, at the initial level, or at the initial stage of our research typically was focused on the technical perspective, right? Because we're engineers, so we are just focused on the technical perspective. And then we did lots of work, maximize output of engineering systems, you maximize reliability, you minimize emissions. And like I said before, we discovered now that even after determining the optimal actions, we often did not get, after determining the optimal decisions rather, we often did not get the optimal corresponding actions. And now that was due to the fact that the social and the economic aspects of the technology wasn't actually being considered. So we have begun to consider some of these aspects, the socio-technical aspects, having to deal with how to maximize technology adoption, for instance, how to minimize impact of technology disruption, how to maximize profit and minimize cost, amongst other interrelated research areas. And the aim again is also to achieve food, energy, and water security. So I would take our time to explain what we've been doing in the mathematical optimization space as a subset of the prescriptive analytics platform. And basically, in the mathematical optimization space, what we seek to do is to determine the optimal course of action considering various technical, economic, and social perspectives. And then now this is a depiction of the flow that we leverage on in our work. So you have an optimization solver that leverages on your objective function, which you either seek to maximize or minimize. You have some data that is either known or some that you might predict from your prescriptive analytics platforms. And then you have your constraints that can either be physical, technical, financial, and social. All of this is fed into your optimization solver, and then you now get your optimal decision. And hopefully you now have corresponding actions, optimal actions. There are a host of research challenges in this area, which we have worked on over the years. The first has to do with non-convex objective functions, and we've leveraged significantly on using evolutionary computation methods and meta-heuristic algorithms. We've done a lot of work using particle swarm optimization, ant colony optimization, exchange market algorithm, and we developed even a sample algorithm that can be used in power systems. There's also the problem of handling uncertainty in data, right? And then two methods can be used to mitigate uncertainty in data. The first is robust optimization, and the second is stochastic optimization. I would have loved to explain what the difference is, but again, I want to keep it simple. And then there's also reliability analysis that we've done a lot of work on, and then scenario analysis, what-if scenarios. We've done a lot of work using sensitivity analysis and scenario analysis. That is when you determine your optimal decision, you have to assume now that circumstances might change. If circumstances change, if scenarios change, how does it impact on the decisions that you obtain? I would pivot a little bit to the role of demand-side management in our research. We have leveraged on demand-side management programs or techniques in our research significantly. My master's and my PhD work was on the use of demand-side management techniques. And demand-side management techniques essentially believes that the customers or the end users in energy systems, in water systems, can play a role in bringing relief to energy systems when the power system is stressed, or water systems when supply is not enough, right? And then we have done a lot of work on demand-side management programs. There are two variants. You have demand response programs and you have energy efficiency programs. We've done a lot of work using these tools in energy systems. And of course, there are lots of parallels in water systems that have also been deployed in our research. These are a couple of some of the works we have considered. And then that we have, I wouldn't go through most of this in detail. What I would just want to highlight is that there is only so much that you can achieve with demand response, right? After some time, the demand response programs don't provide much utility, right? And there is now the need to also consider the supply side of the equation and look for ways of expanding the supply side of the equation. And that's led us to some of the works that we've been doing, expanding the supply side of the equation in energy systems. We've done a lot of work on generation expansion planning, on transmission expansion planning, which basically seeks to expand the power system 10, 20, 30 years into the future, determining the locations where you need to install generators. And we've also introduced concepts of clean energy. And what that means is now that the energy sources that we should be installing now should be clean and should not have harmful gaseous emissions, right? And then we've also looked at it either in the long term, in the medium term, and in the short term. And there are a lot of papers that we have published along these lines. In the agri-food space, we've also leveraged on prescriptive analytics in this space, in the upstream sector, in the midstream sector, in the downstream sector. This depicts a biofuel production process where you have, you collect the raw materials and you store it, and then you have a biorefinery, and then it goes downstream. So we've leveraged on prescriptive analytics to make optimal decisions within this space, within the spectrum. And these are some of the results from our research, or from a handful of results. I can't go through everything, but suffice to say here is that in this example, it shows now where we should construct new power system lines and the capacity that this line actually should be. And then we see now that it provides much needed relief to the power system. These results also show the introduction of demand response programs into economic dispatch, and comparison of the various parameters, fuel cost, emissions, and the rest shows now that demand response programs typically give, on the average, 20 to 40% reduction in demand and provides much more needed security in the power system. We've also done a lot of work I mentioned before using evolutionary algorithms for non-convex optimization problems. And then here we see now where we use the exchange market algorithm for generator maintenance scheduling. and we see now that it provides comparable results with our classical optimization methods. We've also leveraged prescriptive analytics on the energy-water nexus. An example here is a renewable energy power desalination plant in Cape Town, and we basically used renewable energy as an alternative source of energy to power this plant, and we did the analysis, and then the results show now that leveraging on renewable energy power would actually offset the environmental emissions and ensure now that much more power is produced to run the plant, and you also now obtain much more fresh water. The major challenge of seawater desalination is the energy requirement and then the brine management. The brine is the waste product that is produced. So in this work, we also modeled simultaneously the energy management problem using renewable energy, and we also modeled brine management using electrodialysis and crystallization. And those two methods led us to 20% more fresh water and 10% more fresh water, respectively. We've also done a lot of work on the food energy nexus, renewable energy powering agricultural setup for hydroponics, for a farm settlement, for irrigation system, and for livestock. And the results basically show now that you could actually get scenarios that would actually ensure now that the system is reliable and demand is actually met. At the same time, harmful emissions are minimized. This is the result for the energy-water nexus, and it shows here now that when the grid, because of the advent of renewables, the grid does not need to produce doesn't need to produce power any longer, and then you have a green system. You just exhaust all renewable energy sources without having to use power from the grid. And then finally, we've leveraged on prescriptive analytics in the food energy water nexus. This is a case study in Mpumalanga, where we considered what the food resources, the energy resources, and the water resources were in that particular locale. And then we now determined what the processing options were, and then we now sought to now determine what should be the optimal choice of those technologies that would ensure now that there is food and energy security in that domain. We use mathematical optimization, linear programming, and mixed integer programming for this case study. And then our results showed us the particular combinations and the particular quantum of those combinations that are required to achieve food security and energy security. So this shows us the quantum of the various options that we had: dry land open field farming, bioenergy, and undercover greenhouse farming, and the various options that we had. It shows us the best way that these sort of resources can contribute towards food security and energy security. We have there are a host of other outputs that I cannot delve too much in detail, but we have published a book, or two books actually, the optimal operation and control of power systems using algebraic modeling language, which basically details application of prescriptive analytics in the energy value chain: generation expansion planning, transmission expansion planning, economic dispatch, microgrid scheduling, and the rest. And then we've also talked about mathematical modeling in a bit more detail, coupling it with engineering design in another of our books. We've also designed a platform for those that do not necessarily have the domain expertise in prescriptive analytics, whereby you do not necessarily need to understand what goes on behind the hood. You can just basically obtain your data, load it either as an Excel file, or you load it manually, and then you now obtain optimal result for the specific case study of interest. This is an example of a static economic dispatch problem that we have deployed using prescriptive analytics. Moving on to what we have done in predictive analytics, that's machine learning. Machine learning basically is a branch of artificial intelligence, And then we typically use machine learning to predict or classify using data instances. But in this case, we do not explicitly program our algorithms, right? Machine learning algorithms require data to learn from and often require extensive computing resources. This is a flow chart of a sample machine learning project that we worked on, machine learning for water quality anomaly detection. And then we've also leveraged on machine learning for ensemble methods in machine learning. Ensemble methods basically is when you combine one or more machine learning methods, you hybridize them, and then you basically produce much more accurate solutions than a single model would have produced. And these are, we've used case studies of ensemble methods in water systems. We have a deep learning algorithm and an extreme learning machine algorithm that we have used for water systems, and these are some of the results, various ensemble methods and the results that they obtained, and we ranked these ensemble methods based on the accuracy that they produced. We've also used machine learning in the agri-food space. Here we use various machine learning algorithms to predict the performance of a food processing building. Here we've also used machine learning to also forecast heating load and cooling loads for a building, for a smart building. These are the results. I wouldn't go too much into this, but they show now that machine learning can actually be used to predict data well into the future, and this can now also be fed into the prescriptive analytics platform to obtain optimal solutions. The other 4IR technology that we leverage on significantly is the Internet of Things technology. And then the Internet of Things basically is a network of physical objects fitted with sensors that can be used for data gathering, for system monitoring or control, or can also be used for automation. When it is used for data gathering, the data that is gathered can now be fed once more into our prescriptive analytics platform for optimal decision making. Right. The research challenges that we have encountered when deploying Internet of Things has to do with optimal sensor placement. So ideally, you would want to put as many sensors as you would like to, but now there are cost implications for that. So you now need to determine what is the minimal number of sensors that would ensure that you have maximum coverage in any locale. And how do you ensure now that you also minimize the energy consumption of these sensors, right? And how do you ensure now that the data that you transmit is also secure? So we have done a lot of work in this space. An example here is where we used a IoT, Internet of Things, to tackle an efficiency or a reliability problem. So in this case, we discover now that when you have PVs, after some time, when they are exposed to the elements, they suffer from dust, they gather dust, right? And when PVs gather dust, we discover that it can reduce their efficiency by as much as 40%, right? And then most times it's difficult to clean it, so those systems are not able to produce power as much as they should. So we used IoT to develop a cleaning system such that you do not necessarily need to do this manually, and then you can get the required energy that you need for your PV needs. Then we've also used IoT in the water system field. Here we used IoT for water supply monitoring. This was actually, the data that we obtained from this system was actually fed into our prescriptive analytics platform, and we were able to now train a machine learning algorithm to detect anomaly in water distribution networks. We've also used IoT in the food-water nexus in an hydroponic system, right? The hydroponic system allowed us to control the pH in a system at very granular details, right? And then this is a diagram of the final system, and this is the control that was developed for the hydroponic system. A provisional patent was actually obtained for this invention, and it's currently on the road to a full patent application. The final technology that we would talk about is blockchain. Blockchain is a technology that is basically leveraged, like I said, to ensure integrity of data. In instances where trust is an issue, especially around payment, around transactions in food, energy, and water systems, then you need to leverage blockchain to introduce transparency in such systems. And I wouldn't go in detail into how blockchain technology works, but suffice to say is that we've deployed it in energy systems. Here we have a case where you have plant operators that buy fuel from fuel suppliers, right? And then we leverage blockchain in this case where the fuel suppliers will give offers, and then the plant operators will make an order of how much fuel they want to buy, and then we develop the smart contract that will select the offers that should be purchased, and then you also effect payment for the purchased fuel. And then we also use blockchain for peer-to-peer energy trading, depicted here. We've also used blockchain for water distribution network, where we integrated it with IoT to properly manage payments for water consumed amongst a number of consumers. And these are the results that we've obtained. Basically, I'll just talk about the fuel supplier case. What the smart contract does is that it helps us to, it orders the various bids that the fuel suppliers submit, and it enables the suppliers to, it enables the thermal station to choose the supplies that they want, and it orders it according to the cheapest one. So here 40K at 0.09 is the cheapest one, and then it takes all of that first, and then it goes to the second cheapest one that's at 0.092, and then such that it uses the cheapest options first before going to more expensive options. And then we've used blockchain in the agri-food supply chain for livestock, for cattle, and then we basically use it to obtain the age, the breed, the gender of the livestock, and then it moves through the various stages, the backgrounding stages, the feed lot stages. You obtain data about the feeds, about the vaccines. You obtain data about where it's processed, its butchering time, its control test parameters, and then finally up until the point where the livestock is actually sold to the consumers. And this is a depiction of the architecture of the blockchain system that we have developed, and this is the depiction of the platform that has been developed that is actually in the beta testing stage now with my students. In summary, what are the reflections from what we have been doing over the years? The key takeaway I would like to harp on is that integrating 4IR technologies into the food, energy, water nexus is a significant and a critical bulwark for the perfect storm. And there is need to explore other facets apart from the technical perspective, right? There's need to also look at the social perspectives, the economic perspectives, and the interactions between all three perspectives. We initially started with a focus on the resource end users, that's encouraging them to participate in demand-side management programs, and there is need to also increase focus on this area. And at the same time, there's also the need to adapt a more consumer-centric approach. So in food systems, for instance, there's the need to also focus more on smallholder farmers and why they are not oftentimes part of the formal economy. Data paucity, data integrity, and data processing are critical data issues to be considered and mitigated. When you're doing research in Africa, sometimes data is an issue, and the integrity of the data sometimes it's questionable. So how to ensure now that the data is more reliable and you can now be fed into our prescriptive analytics modeling is an issue that should be considered. And finally, there is need for enhanced collaboration between academia, industry, and the government, such that each sector can contribute their quota and eliminate all the bottlenecks in and around the perfect storm. For future work, we are exploring other allied 4IR technologies, GIS. I don't have enough time to expound on why I feel the various ways that GIS is used in modeling now is wrong, but we are working along those lines. We are also exploring computer vision for food processing, and then digital twins and reinforcement learning, integrating them with all our other 4IR technology approaches. We have published a number of works that look at, I mentioned now that we discovered now that the technical aspects, there are lots of solutions there, but other perspectives, either from the social or the economic perspectives, are lacking. And some of our work looks at why is it, for instance, that prepaid electricity meters are not being widely accepted in sub-Saharan African countries, and what is the skill gap for construction 4.0, and how should engineering education change to adapt more to the challenges of the 21st century. We also have a journal publication that tries to provide a platform for research in and around all of these areas where other practitioners can submit their works and, in essence, provide a resource for food, energy, and water studies using 4IR technologies. In appreciation, I would like to appreciate those that have been with me on this journey. Right. I would first of all like to appreciate God. Right. Here I have pictures of my parents and my family, but I don't have a picture of God because that would be difficult to achieve. Right. But I would like to appreciate my parents, and they should have been here, but they were not able to. Their visa application was not attended to on time. Anytime I think of my parents, I think of sacrifice and love. Right. Anytime I think of them, they have sacrificed significantly for me to get to where I am today, and I thank them and I owe them. I would also like to appreciate my beautiful wife and our daughters. They have also been very, very sacrificial. Most times I'm at home, but I'm not at home. Because you're either writing something, or you're reading something, or you're doing certain things. I'd like to appreciate other members of my family, my sisters, my aunts and my uncles, my in-laws, everybody that has supported me in one way or the other. I also like to appreciate my spiritual leaders, my Pastor Joseph Ajakaye, our pastor when we were in Pretoria. I'm sure he's watching here. And I also like to appreciate Pastor Festus Adetunji and his wife for being here. They have also they've played a very instrumental role in my life. I also like to appreciate my supervisors, mentors, and colleagues. Right. So Isaac Newton said, "If I have seen further, it's by standing on the shoulder of giants." Professor Mura Fariogu was my master supervisor, was one that introduced me to demand response. Professor Phillips Abola was the one that taught me about publishing. He was like, "Nnamdi, you need to publish as an academic, and you have to balance quality and quantity." The late Professor Adnan Kashman was the one that introduced me to machine learning. I actually spoke to him a month before he passed on, and I invited him to join the board of our journal, and he accepted wholeheartedly. And he had been a very huge source of inspiration. My PhD supervisor, Professor Shah, he was the main reason I came to South Africa. Right, he has played a very impactful role in my life. The training that he gave us. We are still benefiting from it today. My co-supervisor for my PhD, Professor Zhang, has also been a very huge inspiration. In the University of Johannesburg, I'd like to acknowledge the leadership of the university, the Vice Chancellor of the university, the Deputy Vice Chancellor, and then the Executive Dean, Professor Daniel Marshall. The university has provided a very conducive environment for us to pursue our research. and for that we are very grateful. I'd like to appreciate past and present heads of department of my department. And then I'd like to appreciate Professor Mbowa, Professor Kengabi, Professor Igbaboa. Professor Igbaboa is here. They have been very instrumental in my career. When I joined UJ, I met them and I told them that, listen, what advice do you have for me? And they have been very open, giving me advice, strategic directions along the lines. I would like to also acknowledge Professor Hada, my immediate past HOD, Professor Kowio, who is also here, and Professor Bokoro, Professor Rudolph, who is my respondent, Professor Debo, Dr. Longe, and so many other colleagues. I'd like to also acknowledge my research partners that are not here. They've also played a very impactful role in my life. Finally, I'd like to acknowledge my students, my past and present students. There's no professor without a student, right? And then I'd like to acknowledge my first 4 graduates. These guys and lady, they worked with me at the initial stage when I just joined UJ, and there was no even money to support them. I've had the privilege of supervising students from across the African continent, and I can say now that based on my interactions with them, I'm sure that the future of the African continent is bright. And then I also like to acknowledge a couple of these students. These are not all my students, but these are the students that I started out with new topics. Dr. Dogo was machine learning for water quality detection, Ocampo, desalination, Mrs. Obolumani, food, energy, water nexus, David Love, project management in the food, energy, water space, and Edmond Rotimi, machine learning in the agri-food space. And these are pictures of some of us after a certain outing. Finally, I'd like to appreciate my sponsors, right? The University of Johannesburg, all the various governmental organizations in South Africa and outside South Africa, and our industrial partners, right? We could not have done this without them. Thank you very much for your attention.
Dean Mashao, Chief Financial Officer, Ms. Mamarari, representing the Vice-Chancellor, Prof. Nwulu, and your family, colleagues and friends. In his outstanding lecture, Prof. Nwulu has highlighted the profound changes in the way the food-energy-water nexus has impacted our lives and has drawn our attention to the increasing dangers to our ecosystem. The evidence is clear. The planetary boundaries have been breached. South Africa, Africa and the world are at an historical juncture in which the capacity to live without irreversibly compromising the environmental and biophysical conditions on which life depends is under threat. Despite initiatives such as the 2030 Agenda for Sustainable Development and its related goals, there are still significant challenges and intrinsic trade-off that arise from the interaction of globalization, demographic changes, declining world economies, growing corporate power and influence, all of which escalate the risk of an equitable and sustainable socioeconomic structures and societies. In your lecture, Prof. Nwulu, you have recognized the interconnectedness between the 3 essential resources of food, energy, water, as well as the blending of human and artificial intelligence within a broader ecology, clearly indicating your holistic, integrated, and comprehensive understanding of the complex problems and thus more effective and efficient solutions. This evening, ladies and gentlemen, we heard not an abstract philosophical and technological argument, but one that shows a profound comprehension of the high priority nexus framework and the allied 4IR tools. However, 4IR has been frequently been viewed as complicated and advanced technology. As your wife said, the test of your ability is to make a 5-year-old understand. But many of us have not been exposed to 4IR, and therefore it is sometimes beyond the grasp of policymakers, difficult to implement by managers, a lack of high-end skills, and a concern about the unknown. Many people still question the potential efficacy of this technology, the return on investment. Show us the evidence, they ask. We need more data and options. I also believe that due to the hegemony, power, politics, and fixed mindsets, people remain resistant to change. Our inaugural speaker has presented the evidence. He has illustrated systems which are fit for purpose and which were shown that humanity cannot remain locked into its destructive path. His comprehensive and insightful lecture validates the view that the available knowledge and broad application of 4IR is not a theoretical construct, but rather comprising highly intelligent systems that can be translated into practical tools and mitigate the storm and bring about wide transformative change with end users. In the process of problem solving, which we all face, good decision making is indispensable. Prof. Nnamdi, you have emphasized the importance of optimal decision making through your descriptive, diagnostic, predictive, and prescriptive analyses, all key instruments in ensuring accuracy and reliability of future options. Your reference to the causes of the perfect storm highlights the precarious state prevailing on the African continent and the urgent need to address these challenges. The case studies and examples you have given are important in shifting mindsets and offering interventions which are contextually relevant and can have positive consequences, particularly scaling potential, economic viability, and promoting sustainable development. These interventions would support and achieve more meaningful and better lives for our urban and rural end users, as the nature, volume, and dimensions of the food, water, energy resources differ from one geographical location to another. The application of the 4IR tool, nevertheless, remains constant and produce consistent and cost-effective results. Prof. Nwulu, you have given us hope and confidence to tackle these programs with courage and conviction. With the compelling evidence you have presented, we can transform the destructive storm with positive and transformative outbursts and waves of energy, commitment, and collaboration to which you referred. This collaboration with academia, industry, and government, in conjunctions with the systems to which you referred, can lead to effective and efficient smart industries, smart health, smart transport, and smart cities. It was only this afternoon at a meeting with the mayor and other executives that the idea of Johannesburg becoming a smart city is so critical. And I think, Prof. Nwulu and your colleagues, we have got a job to do in Johannesburg. You mentioned that Prof. Beddington showed that the storm could make landfall in 2030, only 8 years from now. Thus you, or shall I say we, all of us, have an enormous and immense task to accelerate the application of systematic transformation that will develop equitable and sustainable solutions using the deep reservoirs of skills and expertise which must be made more available and accessible and affordable to a wider community. The University of Johannesburg, with the strong leadership of our Vice-Chancellor, Prof. Mawala, is at the forefront of this endeavour. And you, Prof. Nwulu, and your team have played and can continue to play an important role in this regard. By transforming the Bulwark concept, Prof. Nwulu has displayed an actualization of an inspiration and has made an initial idea real, relevant, and applicable through hard work and dedication. As Victor Hugo said, and I quote, "There is nothing more powerful than an idea whose time has come." The presentation describes the creation of a bulwark, a protection from the perfect storm. On the other hand, Prof. Nwulu has suggested not only an antidote and a defense mechanism, but he has offered a forward-looking future work to further refine, enhance, and improve his expertise and his systems for the good of mankind. Prof. Nwulu, your work shows that it is indeed possible to change our world for the better. Wishing you every success and God's blessings. Thank you.
Ladies and gentlemen, I think another big round of applause for Professor Nwulu. You shared with us very sobering statistics of the challenges that the world is facing, Professor Nwulu. But I think it's comforting and assuring to know that now that the world needs scholars like yourself to help us navigate and find solutions to these very difficult problems. We do have people like you who are dedicated to this work and to also producing many more scholars to ensure that we find these solutions. So congratulations again. And on behalf of the University of Johannesburg, we wish you all success that you deserve to ensure that this work finds its impactful meaning. Ladies and gentlemen, we have now come to the end of our proceedings for this evening. Thank you very much for being part of today in honoring Professor Nwulu. We do have refreshments that will be served next door. Please do join us. And thank you very much, particularly to your family, Professor Nwulu, and well done once again.